Alright guys, I'm going to give you a quick pre-lab lecture here over scientific measurements. And we're going to run through some very basic, quick, standard definitions here to get things rolling. Even though the title of this lab is statistics, even though the title of this lab is measurement, it really boils down to a lesson on error. And in order to talk about error, we need to define a couple terms. The easiest way to do this is to talk about target shooting. Three archers are shooting at my target here. My first archer, we'll call him Malcolm Merlin, shoots 3 arrows. My second archer over here, we'll call him Adrian Chase here. Shoots 3 arrows, and his 3 arrows land like that. And then our next archer, whoops, that's going to have trouble showing up. Our next author, we'll call him Oliver Queen. Shoots 3 arrows, and they go like that. And then we'll have one more here. We'll have Thea Queen, and she'll shoot 3 arrows, and her arrows will go kind of like that. Which of these archers is the best shot? Now, the answer to this really depends on how you define a good shot. What is the objective of shooting arrows? Well, you're saying, of course, that the objective of shooting arrows is to get as close as possible to the bullseye. So we want all our shots within the bullseye. We would define this closeness to the bullseye as the accuracy of our archers. Accuracy is the term used in science to describe how close a measurement is to the accepted or true value. In other words, how close the arrows are to the bullseye. If we look at our archers, we can see that 2 of them wound up fairly close to the bullseye. Right? Our Oliver Queen here got all 3 shots in the bullseye, and then Thea Queen, she got 1 shot in the bullseye and then 2 really close by it. So we could say that Oliver Queen shots were very accurate. And we could say that Theaqueen's shots were also very accurate. But is that all you want when you're shooting or taking a measurement? Do you just want your measurements to be close to the correct value, or do you want them close to each other? For example, here, let's take a look at Theaqueen's, the red dots. She got one shot directly in that bullseye, and two others close to the bullseye, but are they close together? No, those shots are all strung out, yes? So would you want her shooting an apple off your head? No, because there's a 1 in 3 chance she's going to miss your head altogether and miss the apple altogether and hit something more crucial, yes? So even though we would say that she's very accurate, because those shots aren't close together, there's still a problem with that measurement. The concept of getting repeated measurements close together is a concept we've met before, and that's known as precision. How close repeated measurements are to each other. That's referred to as precision. If we look at our target here again, we can see that Theaqueen, even though she was very accurate because her arrows all fell close to that bullseye, her arrows weren't very close together. So we would say that she was accurate, but not precise. Oliver, on the other hand, our green arrows, all 3 arrows are in the bullseye, so he's accurate, but the 3 dots are also very close together. If we were to take a dollar bill, if we were to take some money out of our pocket, we could probably lay a dime on top of all 3 of his arrows. So we would say he is precise. We would say he's accurate, and he's precise, because his arrows are close together. If we look at our other 2 archers, Malcolm Merlin and Adrian Chase, Malcolm Merlin here, the 3 black dots, all of his dots are close together. That means he's precise, but his 3 dots aren't anywhere near that bullseye. So he is precise, but not accurate. Then we have Adrian Chase over here. And Adrian Chase, we have 3 arrows. The 3 arrows are nowhere close together, and they're nowhere near the bullseye. So they're not precise, and they're not accurate. So those are conceptually the terms we're trying to define here. And I guess, or at least I'm hoping, if you do recognize these names, we are going to be so best friends. Why don't you write down the word arrow? Everybody write down the word arrow for me. Everybody write down the word arrow. All right. First thing we want to talk about is error. Error is the difference between the measured and the accepted value of an experiment. What do we mean? Well, let's take a look at a very typical lab example. A student measures a volume of her unknown as 41.2 milliliters. The accepted value of the unknown, in other words, what her teacher has on the answer key, is 42 milliliters. Your error is the absolute value of your measured minus your accepted. So the student's error would be 41.2 minus 42, or 0.8 milliliters. That would be her error. Now, is that good or bad? Well, we like to think in terms of percents as people, right? That's how we give our grades. Did you get 100%? Did you get 10%? So people like to think in terms of percents. Therefore, we frequently measure error using a statistical indicator known as percent error. Percent error is the absolute value of the measured minus accepted divided by the accepted times times 100. So for our student here, her percent error would be 41.2 minus 42.0 divided by 42 times 100 equals 1.9%. And that's all there is to percent error, right? Chemistry is easy, life is hard. We now need to define a couple other terms. There's more than one type of error. We can divide error into a couple different categories. We can define error into two broad categories: random error and systemic or systematic error. Random error is error that is exactly what it sounds like. It's error due to random factors that we have no control over, and it's not mathematically repetitive. It's the type of error that's impossible to eliminate and very, very difficult to deal with. Systemic error, on the other hand, is error that is repetitive and constant. For example, our student in our last example, if every single time they measured their volume, they were off by 0.8 milliliters, that would be an example of a systemic error. If the error is the same every time, then it's systemic error. If the error is different every time, then it's random. Systemic error can actually occur in two different ways. This repetitive error can be repetitive either as a set value, Systemic error can be repetitive either as a quantity or a percent. When it's a quantity that's always off, we define that as absolute error. In other words, back to our student measuring volume. If every time that student measures a volume, it's always off by 0.8 milliliters, that would be an absolute error. If she measured 200 milliliters and it was off by 0.8 milliliter, it would be off by 0.8 milliliters. If she measured 2 milliliters, it would be off by 0.8 milliliters. Absolute error is the same value every single time. Why don't you write down black canary? Everybody write down black canary. The other type of systemic error is relative systemic error. And this is the one that's a little bit harder to understand. Relative error in relative error, the percent error is the same every single solitary time. For example, if our student had relative error, then her measurement would be off by 1.9% every time. That would mean a different absolute value, right? Because if our student measured 200 milliliters, then her error would be that she was off by 3.8 milliliters. And if she was measuring 2 milliliters, she'd be off by stylus stopped working. She'd be off by 0.038 milliliters. So with relative error, the percent that she's off stays the same at 1.9, but the absolute quantity that she's off on her measurements changes. whereas with absolute error, the quantity stays the same. Also, something that should be noted, with systemic error, the direction of the error always stays the same. What do we mean when we talk about direction? We're not talking about that she always goes right or she always goes left. We're talking that her measurements will always be too low or too high. For example, in our little scenario here of our graduated cylinder, she would always be too low. She'd always be under measuring the volume. So for systemic error, the direction of the error is always the same. Now let's talk about the problem of categorizing these two. With a systemic error, we can actually correct for systemic error mathematically. If we know our value is going to be off by 2%, we can always mathematically correct for that 2%. Random error, we can't really deal with. Therefore, we have to have another way of expressing it. And that's where our things get a little bit fuzzy. How do we deal with random error statistically? Well, the first task is to quantify random error. We actually measure random error as a function of precision. We take repeated measurements of the same thing and then take the standard deviation. So random error is really a function of the standard deviation that we talked about a couple lectures ago. We express random error using what's known as confidence intervals. See how everything's tying together from last lab? We could also refer to these confidence intervals as the uncertainty in our measurement. For example, if our lab student had measured the volume of water using several different graduated containers, and she discovered that she had a standard deviation of her repeated measurements of an average of 42.1 milliliters with a standard deviation of plus or minus 3 milliliters, 0.3 milliliters, we could say that she has a random error of 0.3 milliliters. Her confidence intervals, therefore, or her uncertainty, we'd have an uncertainty of plus or minus, let me make very clear my definitions here. We would say that she has an uncertainty of plus or minus 3 milliliters. We would have confidence intervals for this measurement of 42.4 milliliters on the upward side and 41.8 milliliters on the downside. And I know I used a different volume, so she's measuring something different. On the downward side, right? So that would be her confidence intervals. Why don't you write down speedy? Everybody write down speedy. All right, let's talk about the experimental portion of this lab. The first thing I want to make quite clear is we're skipping experiment 1. Not skipping experiment, we're skipping activity 1. It's really poorly designed, lots of issues with it. It caused lots of heartache for the one class that I had do it simply because it's nonsensical. Most balances weigh the same every time. So we're really going to skip 2. Skip 1, and we're going to move to 2. So let's take a look at activity 2 here. All right. In activity 2, they're telling you to read the level of water in a graduated cylinder. And they're telling you to express the upper limit and the lower limit. And they're asking you to put that on your paper. If you look at data table 2, they ask for the high internal volume and the low internal volume on that data chart. Let me pull in that data chart for you real quickly here. I know this is exciting for you. Ah, shoot. Even more exciting when I hit the wrong buttons and take forever to get to it. All right. So now we've got data table 2. And they talk about in data table 2, well, let's just go through the experimental together. See, this is almost like watching me live. If you have your instructions printed out in front of you, we're on activity 2, labeled B, determination of uncertainty in common glassware. And they tell you to get out a 10 milliliter graduated cylinder, add 7 milliliters of water to it. So you've got that graduated cylinder, you've added 7 milliliters of water to it. All right, so let's talk about how to read a graduated cylinder. You've put 7 milliliters of water in your graduated cylinder according to your instructions, if this was your 10 milliliter one, and that's what your picture is showing you. Unless you are going to spend your entire life, which would be a waste of time, trying to get exactly 7 milliliters in there, and by the way, you would fail. Matter of fact, I had a college professor for a lab instructor once who would fail anybody who gave them a 7.00 or whatever on a graduated cylinder reading, accusing them of either wasting time or cheating. So your objective when it says 7 milliliters on that graduated cylinder is to get as close as possible to that 7 milliliters and then read what you actually have. Now, when you read a graduated cylinder, if you look at your water level, you'll notice that the water lies along a little curve. Now, because this is a perfect illustration land, it looks like it's a big old curve there. In reality, your curve for a graduated cylinder, particularly the larger ones, is going to be much milder. Probably barely visible to the eye. But you have that curve there nonetheless. And for water, the curve is an innie. And that curve is referred to as the meniscus. That is a word you need to be familiar with. Just like the thing in your knee that athletes are always tearing, right? Meniscus, the downward dip there. By convention, you always measure the volume of a liquid from the bottom of the meniscus. To read this volume, and when I say read this volume, we're going to talk about the volume that would go right there for the volume of water. To read this volume of water, you would come over here and you'd go, okay, it's at least 6 milliliters, 6.1, 2, 0.3, 0.4, 0.5, 0.6, 0.7. So we know it's at least 6.7. Then it is considered good and proper form to estimate the tenth. Now this is where I disagree with your authors. Your authors say that it's 0.5. I don't think that's anywhere near 0.5. I think it's actually closer to a 0.3 or 0.4 if I was reading it. But that's how you would record the volume. 0.3, 0.4, something like that. So you'd say 6.73 for your actual volume there. What do they mean by your high interval and your low interval? This is where I begin to disagree with your book, but I'm going to go ahead and tell you how to fill in this chart so you don't get confused. Then I'll talk about where I disagree or agree. Because that last digit's an estimation, they say that you have a low estimate of the line right below the meniscus and a high estimation of the line right above the meniscus. So they would say that, well, that didn't help at all. Drew way too large here. Let me blow it up a little bit. This is so cool. I love my toys. They would say that this line right here is your bottom level. So your low interval would be 6.7. Your high interval would be the line right above your meniscus. So your high interval, and let me use a different color here. Your high interval, I know, I used blue to circle on blue. Brilliant. Your high interval would be that line right there, right above. So your high interval would be 6.8. So they would say that your uncertainty is... They would say your uncertainty is the difference between your high and low interval divided by 2. So to figure out this uncertainty on your chart, make it small. Come on, just a second. Oh no. Oh no, Mr. Belt, what did I do? I'm grabbing every object I want to except the one I want to. You go away. I'm trying to get you now. There we go. And you go back to where you belong. Once belong. Alright. According to your lab instructions, and this is on your lab instructions on page 5, your uncertainty is equal to the quantity your high interval minus your low interval divided by 2. So our high interval here for this experiment would be it's not going to let me move things easily. Darn it. My high interval here would be 6.8. My low interval would be 6.7. And I'm dividing that difference by 2. So that would be 0.1 divided by 2. And that would give me, follow the blue pen, 0.05. And because it would be plus or minus, because it could be either higher or lower than the value I measured. So our uncertainty would be plus or minus 0.05. And what that value does is it takes into account, it makes the assumption basically that you have a potential 100% rounding error in this last sig fig. So that's where that uncertainty comes from that you see reported often. You'll see this uncertainty actually stamped on some glassware. So that's how you calculate the uncertainty. Something else they told you to do was they told you to take the mass of your empty graduated cylinder and your mass of the glassware and water. How do you think you're going to get that mass of water? Well, if you weigh the empty graduated cylinder and you get, I don't know, I'm going to come up with a totally improbable value here. I'm going to say it's 50.2 grams for my value there. Oh, by the way, I've been naughty. I should be including units, because if you don't include units, I would so count you off. Now the mass of the graduated cylinder plus water, you'd record down here. How do you think you get that mass of water there? That mass of water would be the mass of the cylinder plus water that you just took minus the mass of the cylinder empty. So in this experiment that we just talked about, 56.9 minus 50.2 equals 6.7, it looks like. So that would be 6.7 grams. Are we good on how we're going to fill that in? You're going to repeat this process now for your 50, your 25, and your 250 milliliter beaker. Why don't you write down Mr. Terrific? Everybody write down Mr. Terrific. Speaking of which, am I the only person highly frustrated by the fact that all over Aero we see signs for Cord Industries and they haven't introduced the Blue Beetle? Seriously, Ted Cord was like my favorite Blue Beetle. In my 6th grade art class, we had to turn in a final project, and I drew a life-size portrait of the Ted Cord version of Blue Beetle. I loved Keith Griffin's Justice League International. If you haven't read it, take the time, read it. Well, talk about getting off topic. Let's move on. Alright, now let's go on to Activity 3. And in Activity 3, we're actually using the experimental data from Experiment 2. We're just copying in some of those values. For example, for our 10 milliliter graduated cylinder, I'm taking that 6.7 grams of water that we measured from the bottom of Table 2 in the last experiment. And what we're going to do is we're going to calculate what the volume should have been compared to what we read it as. Remember, we read a volume, even though it doesn't appear on this chart, we read the volume to be 6.73 milliliters. We calculated its mass, however, at 6.7. What we want to do is we want to get the true volume of water we had there. The density of water changes as a function of temperature. So the first thing you're going to have to do is take the temperature of the water. Now, it should be somewhere between, probably, depending on your house or wherever it is you're working, somewhere between 18 degrees Celsius and 25 degrees Celsius. Quite frankly, if you're at 18 or 25, you're either really cold or really hot. But you're somewhere between those temperature ranges, probably for your water temperature. Let's make it easy on ourselves. Let's say that the temperature of our water in this scenario is 22.3 degrees Celsius. We need to find the density of water at that temperature. So what we're going to do is we're going to pull up. It's not letting me manipulate. There we go. We're going to pull up our density chart here. And we said 22.3. So we're going to find temperature 22 on our chart. And this is the table from your lab manual. See temperature in Celsius, temperature 22. And we said 0.3. So we're going to go along this 22 column until we find the 0.3. See the 0.3? And see the 22? I'm going to have trouble keeping things straight, so I'm going to draw a little line here. And where are we? Okay. We've got the 22. We're going to go along the 22 until we get to the 0.3. And there we are at the 0.3. So that would be our density, 0.997 grams. So where it says density of room water, I'm going to write in that 0.997 grams. And it's density, so it's grams per milliliter. We now need to calculate the actual volume of the water. The actual volume of the water here is going to be our mass divided by our density. Remember that. Volume equals mass divided by density. So it's going to be that 6.7 divided by 0.997. Get out my calculator here. Let's do the math. 6.7 divided by 0.9977. And that's a 9 right there, right? Everybody can tell that's a 9 now. 9. And there, that actually gives us 6.7. And here's where we want to do it a little bit differently. To make life interesting for us, I want your number of sig figs to make sense to you. So we're going to go 6.7 is what our sig fig rules say it should be. Let's carry one more here. 6.715 is what your calculator will tell you if you've been doing this along with me as a home gamer, which I hope you have been. I'm going to make it 6.75 there, right? Oops, no, 6.72. 6.72. So we've got a mass of 6.7, a volume of 6.72 milliliters. So our calculated volume is 6.7, and we're going to write that 2 as a subscript to let ourselves know that it's not a significant figure. One thing I wish they had for this, matter of fact, I'm going to add another column onto this chart before I give it to you that's not in your, that'll be in your lab report template but not in your lab report instructions. I'm going to add a column for percent error. And what you're going to do, alright, so we've added in our column with percent error that you'll see on your report template here. Let me scoot this down just a little bit. How are you going to calculate this percent error that I decided to dump on you? Well, I'm going to want the percent error for every single solitary, oh my word, stop that. Not you, the computer. Where was I now? You're going to calculate this percent error using the following formula. You're going to use percent error is going to equal your calculated volume minus the red volume. And that won't be on this chart. That will be on your other chart. Divided by your calculated volume times 100. So for this experiment, we had a calculated volume of 6.7 sub 2 milliliters minus a measured volume of 6.73 milliliters. We're going to take that difference and the absolute value of the difference. Then we're going to divide by our calculated volume, 6.72, and multiply by 100. And we're going to get a very small difference here. We're going to get 0.01. So you can follow my calculations. I'm going to scoot that over just a little bit. 0.01 divide by 6.7 sub 2 milliliters times 100. equals 0.1 0.15%. So that would be our percent error for our graduated cylinder in our mock experiment. And I want you to give me the percent error for your 50, your 25, and your 250. And that's all you're doing in today's experiment. Why don't you also write down the atom? Everybody write down the atom. That's it. Beep.